Problem 19. If f of xy is equal to k times y minus x is a joint density function over the triangular region with vertices at 0, 0, 0, 1, and 1, 1, then what is the value of the constant k? Okay, so problem 19, we're given a joint distribution over a triangular region with certain vertices. So it can be, this is the graph of what we're doing here. And we need to find the k that makes this a true density, meaning it integrates to 1. So we know that if we integrate over all possible values that it equals 1. So 1 is equal to, and note that if we're going to integrate with respect to y first. So x has free range, but y must go from x to 1. So now it integrates. So with respect to y, we get this, plug in our limits of integration, and we get this. Now let's integrate with respect to x, and we get this, minus, and then minus of minus is plus. Limits of integration from 0 to 1. Plug those in, we get k is equal to this. That means k times 1/6, but we know that this all equals 1, so k is 6. Problem 20. If x is a random variable with mean mu and variance sigma squared, then mu minus 2 sigma is called the lower 2 sigma point of x. Suppose a random sample of 4 is drawn from the chi-square distribution with 2 degrees of freedom. What is the lower 2 sigma point of the sum of these 4 variables? So sample exam 1 of 8, problem 20. We want to find the lower 2 sigma point of the sum of the 4 variables. So notice first of all that if x is chi-squared with v degrees of freedom, the expected value of x is v, and the variance of x is 2v. So now let's let xi be a chi-square with 2 degrees of freedom, and that's given in the problem. Let's let y be their sum from 1 to 4. So the theorem says that if we're adding independent chi-squareds, it's also a chi-squared with the degrees of freedom added. So this is a chi-squared 8. So the mean of y is 8, because it's the degrees of freedom, and the variance of y is 16, 2 times its degrees of freedom. So mu minus 2 sigma would be 8 minus 2 times 4, which is 0. Problem 21. The moment generating function of x is alpha over alpha minus t, where t is less than alpha, and alpha is a positive constant. What is the variance of x? So problem 21, we're given a moment generating function, and we want to find the variance of x. So the formula that you need to remember, the variance of x is equal to the expected value of x squared minus its mean quantity squared. So to find the mean, which is the expected value of x, that's the first derivative of the moment generated function evaluated at t equals 0. So we need to take the derivative of this with respect to t, and we get this. Now evaluated at 0, we get 1 over alpha. Now to calculate the expected value of x squared, that's the second derivative of the moment generating function evaluated at t equals 0. So we get this, evaluated at 0, we get 2 over alpha squared. So the variance is the expected value of x squared minus the mean squared, so we get 1 over alpha squared. Problem 22. A large wooden spoon is laid in strips 2 inches wide and with a negligible space between the strips. A uniform circular disc of diameter 2.25 inches is dropped at random on the floor. What is the probability that the disc touches 3 of the wooden strips? So problem 22 is we're given a wooden floor with 2-inch strips and a disc with diameter 2.25. Now, if this is our floor with 2-inch slats, and this is our disc with 2.25, let's focus on that leftmost point. So then when you flip the disc onto the floor, that the leftmost point, remember it's uniform, so it could be anywhere, has to be somewhere in order to overlap or to touch 3 boards. Well, it's 2.25, so that leftmost disc has to be within 0.25 of the last piece of the board. So if this is total 2, and it has to be within that little strip, then the probability that touches 3 strips is 0.25 over 2. Now you might say, well, what if it lands on this board and over? It could land anywhere, so it's all normalized. So we can just isolate 3 boards because of the uniformity. So there's the answer, 1/8. If f of x given theta is equal to that, what is the size of the type 2 error in testing the hypothesis that the null is theta equal 1/2 against the alternative that theta is equal to 3/4 using a single observation and the interval x greater than or equal to 1 as the critical region? So problem 23, we have a single observation, and we want to calculate the the type 2 error, probability of a type 2 error. So note that is the probability that we accept the null, given that the alternative is actually true. So it says the critical region is x greater than or equal to 1. So the acceptance region is less than 1. But remember, that's under the alternative, that means that theta is 3/4. So we plug in, we integrate less than 1. So that's 0 to 1 of this density. We get this. So it's 7/16. Problem 24. If the probability R is 1/6, probability S is 5/12, and the probability of R given S plus the probability of S given R is 7/10, then what is the probability of R intersect S? So here we need to find the probability of R intersect S. We're given this equation equals 7/10, but let's rewrite each of those as R intersect S over probability of S, and this is R intersect S over the probability of R. Well, these two, it can be factored out, and then we're left with 1 over probability of S plus 1 over probability of R, which we're given. So then you can solve that for the intersection, and it equals 1/12. Problem 25. If f of x equals 1/2 for absolute value of x less than 1, and y equals 3x plus 2, then the variance of y is... So problem 25 we want to find the variance of y, which is 3x plus 2. So, well, let's find the mean of x, which is 0. It's a symmetric distribution from -1 to 1, so that has to be it. The expected value of x squared, well, let's find it. And we integrate from -1 to 1, and we get 1/3. So the variance of x is expected value of x squared minus its mean squared, which is just 1/3. So now to find the variance of y, which is a linear combination of variables, so plug in the 3x plus 2. Now note that the variance of any constant, added or subtracted, it doesn't impact the variance, so that can go away. And a constant times a variable comes out as squared. So this can be rewritten as 9, the variance of x. Well, we know the variance of x, it's 1/3. So it's the variance of y is 1/3. So here, since it is a uniform distribution, some of, going from A to B, some of you will just know that these are the mean and variance formulas. I didn't, so I had to find the variance. Problem 26. X tosses 2 fair pennies, Y tosses 3, and the winner is the one who tosses the greatest number of heads. In case of a tie, the game is continued under the same rules until a winner is determined. In order to make the game fair, how many dollars should Y wager to each $3 that X wagers? So problem 26 is Y tosses 2 fair pennies, Y tosses 3, and we want to find that that we have a winner. So I give 2 different solutions here, which may help, may not. So here we want to find the probability that X wins. Okay, so I introduced the variable Y, which is the number of heads out of 3 tosses, but I sum over from 0 to 3, so all possibilities. So this doesn't affect our wins. And then we can rewrite this joint as the conditional of the probability that Y is equal to I times the probability that X wins, given that Y is equal to 2. Well, if we know the values of Y, what they are, then we know what X needs to win. So we can go through those possibilities. There's only 0 to 3, so there's not very many. So let's let I equals 0. So Y rolls 0 heads out of 3. How can X win? So that's if he rolls a 2, a 1, or a 0, and he wins later. So that's what we do. So the probability that when Y is 0, it's the probability that X equals 0, but he wins. It's kind of a reset. He has to win starting the next flip. But he could also win when Y is 0 and X is 1, Y is 0 and X is 2. So then we increment it to Y equals 1. And how can X win when Y is 1? Well, if X rolls a 1 and then times the probability that he wins on the next roll, and then X could also just roll a 2 and then win outright. And then when X or Y is 2, how can X win? That's if he rolls a 2 and wins the next time. Well, all these can be calculated. So the probability that Y rolls a 0 out of 3 is 1/8. The probability that X rolls a 0 is 1/4. And of course, we don't know what the probability is that he wins. X equal 1 is 1/2. X equal 2 is 1/4. And then we go to this one. The probability that Y1 is 1 is 3/8. Probability that X rolls a 1 is 1/2 times probability that wins that we don't know. Probably he rolls a 2. And then for this piece is right here. Rolls a 2 is 3/8. Rolls a probability that X rolls a 2 is 1/4 times probability that he wins. Now we can do some math here. So simplify this side to 6/32 times 10 divided by 32 times probability of wins. Well, we can take that to the other side, factor out probability that X wins, and we get probability X wins is 3/11. Now here's a second approach that may be helpful. So if we look at the probability that X beats Y. So this is not, tie's not possible, just that he flat out beats Y. So this is the probability that X or Y rolls a 0, but X has to have a 1 or a 2. If Y rolls a 1, I have to have a 2. And that's the only possibilities. Because if Y rolls a 2, then we can't flat out win. If he rolls a 3, then we can't win. So this is the probability that we definitely win on any given roll. Now, what's the probability that we tie on any given roll? So when Y is 0, X has to be 0. When Y is 1, X has to be 1. When Y is 2, X has to be 2. So each of those probabilities is 5/16. So now if we think about this, probability that X wins is this. So now we're going to introduce a variable called roll. And roll goes from 1 to infinity. So this doesn't affect the probability that X wins because we're summing over all possible X's. Well, this can be rewritten as the conditional probability that we're on roll I times the probability that X wins given that we win on roll I. Well, the probability that we're on roll I means that we tied I minus 1 times, and each event is independent. So it's just the product of those 5/16 raised to the I minus 1. Now the probability that we win, given that we win on roll I, is 3/16. So this can be rewritten as an infinite sum, and that's a geometric series, which is this, and then simplifies to that, and we get the same value. The probability X wins is 3/11. So number 26 26 is continued. So, well, the probability that Y wins is going to be 1 minus 3/Y. That's 8/11. So now the expected return is how much money you bet when you win minus how much you bet when you're expected to lose. And to be a fair game, you set that to 0. You can solve for t. T is equal to 8.